Today, we are going to discuss about the heat capacity at constant volume in terms of partition function. We know that heat capacity is the amount of heat energy required to rise the temperature of a given object by 1 degree or 1 Kelvin. Here, we consider the heat capacity at constant volume, that is, the volume is fixed so that no work of expansion is done, which means all the supplied heat directly increases the system's internal energy U, so that the heat capacity at a constant volume Cv can be written as dou U by dou T at a constant volume V. In terms of partition function, internal energy is written as U is equal to nkt square into dou ln Z by dou T at constant volume V. Differentiating with respect to temperature is often complicated, so in statistical mechanics, it is much easier to differentiate with respect to beta. Almost every partition function is naturally written as Z is equal to sigma I e raised to minus beta ei. So we convert every temperature derivative into a beta derivative, where beta is equal to 1 by kt. Differentiating this equation with respect to t, we can write dou beta by dou t is equal to minus 1 by kt square. Using the chain rule, we can write dou by dou t as dou by dou beta into dou beta by dou t. That is, on substituting the value of dou beta by dou t in this equation, we can write minus 1 by kt square into dou by dou beta. Now, substituting the value of dou by dou t in u, we get u is equal to nkt square into minus 1 by kt square dou ln z by dou beta. Kt square and kt square terms will cancel out each other, so we get u is equal to minus n into dou ln z divided by dou beta. Now, substituting the value of u in the equation of Cv, we get minus Cv is equal to minus n into dou by dou t into dou ln z by dou beta. Now, substituting the value of dou by dou t as minus 1 by kt square, we get minus n into minus 1 by kt square dou by dou beta into dou ln z by dou beta. Now, Cv is equal to nkt square dou square ln z by dou beta square. Now, we are differentiating ln z with respect to beta, that is dou ln z by dou beta is equal to 1 by z into dou z by dou beta. Again, differentiating this value with respect to beta, that is dou by dou beta into 1 by z into dou z by dou beta. Here we have to use the product rule. So in order to use the product rule, let us consider 1 by z as u and dou z by dou beta as v. We know that according to the product rule, d of uv by dou beta d beta is equal to u into dv by d beta plus v into du by d beta. Now, substituting the value of u and v into this equation, we get the first term as 1 by z into dou square z by dou beta square, and the second term as minus 1 by z square into dou z by dou beta the whole square. So we can write dou square ln z by dou beta square is equal to 1 by z square into dou square z by dou beta square minus 1 by z square into dou z by dou beta the whole square. Now substitute this value of dou square ln z by dou beta square into Cv. Then we get Cv is equal to n by kt square into 1 by z into dou square z by dou beta square minus 1 by z square into dou z by dou beta the whole square. Now let us consider that z dash is equal to dou z by dou beta and z double dash is equal to dou square z by dou beta square. Substituting these two equations into the equation of Cv, we can write Cv as Cv is equal to n by kt square into z double dash by z minus z dash by z the whole square. So we can write the heat capacity in terms of partition function, heat capacity at a constant volume in terms of partition function as Cv is equal to n by kt square into z double dash by z minus z dash by z the whole square.